Hi, I'm Anthony Pun, a CS PhD student at Georgia Tech. I present our joint work with Intel where we discover 3 generalizable architectural design principles that enable adversarially robust CNMs. We call them robust principles. Specifically, these 3 principles are optimal range for depth and width configurations, preferring convolutional over patchify stem stage, and robust residual block design by adopting squeeze and excitation blocks, and non-parametric smooth activation functions. The main motivation of our work is to unify the wide range of divergent opinions on how architectural components affect robustness. There were no concessions until our work. The first principle is optimal width-depth ratios. Instead of studying a fixed depth and width configuration in each stage, we aim to provide a flexible compound scaling rule of the relationship between robustness and total depth and width. We find the optimal range for the width-depth ratio is 7.5 to 13.5. A marked robustness gain is achieved by simply redistributing depth and width to satisfy the optimal range. Our second principle is preferring convolutional over patchify stem stage. We compared convolutional stem with postponed downsampling and patchify stem with patch size equal 2 or 4. Both designs show better robustness than the baseline res than 50, but convolutional stem is significantly higher than patchify stem. The reason that the convolutional stem outperforms patchify stem is due to its less aggressive stride-to downsampling and overlapped convolutional kernels. Our third principle is robust residual block design by adopting squeeze and excitation blocks and non-parametric smooth activation functions. Squeeze and excitation block was proposed to adaptively recalibrate channel-wise feature responses by modeling interdependencies between channels. Our experiments on ImageNet shows that the original SE block markedly increased PGD and clean accuracies compared to res than 50. In terms of the activation function, we study ReLU, the smoother variants of ReLU, and parametric activation functions. We find that non-parametric smooth activation functions are significantly better than ReLU, and for parametric activations, both PReLU and PCLU are inferior to their non-parametric counterparts. Thus, we recommend non-parametric smooth activations and replace all ReLUs with CILUs. Our 3 design principles generalize across a wide spectrum of dataset scales, adversarial training methods, model parameters, and network design spaces, providing consistent and notable adversarial accuracy improvements. In particular, our RAWRN7016 achieves 71.01 accuracy, which is the top on RobustBench. On ImageNet, we show a significant improvement over res and 101. Our findings unify prior work's divergent opinions on how architectural components affect robustness and highlight the benefits of exploring intrinsically robust architectural components. Our architecture currently ranks first on the RobustBench CIFAR-10 L-Infinity leaderboard, with a 71% AutoAttack robust accuracy. Our code is publicly available.